Good afternoon, and welcome to today's Microwaves and RF Design and Electronic Design webcast. Our topic today, Development and Deployment Strategies for Xilinx RFSoC FPGA, sponsored by Pentec. I'm Carlos Gonzalez with Informa's Design, Engineering, and Sourcing Group. To begin, let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during today's session, simply hit F5 to refresh your webcast console. If you want to resize the presentation windows, please click on the lower right-hand corner and drag to your desired window size. If you need assistance solving common issues, please click on the yellow help icon below the slides. Additionally, we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. To do so, simply type your questions into the question window on the side of your screen and hit the Submit button. Now let's meet today's speakers. Bob Sandura serves as a product manager for Pentec's DSP, data acquisition, digital receiver, and software products. Rodger H. Hosking is a vice president and co-founder of Pentec Incorporated, where he is responsible for new product definition, technology development, and strategic alliances. Paul Messaboff is co-founder of Pentec and holds the position of vice president of engineering. Now let me turn things over to our presenters. The floor is yours.
Thanks very much for the introduction, and thank you everybody for joining us today. Today we're going to cover several aspects of the RFSoC technology, which is going to be broken down into some hardware overview, some product strategies, hardware products, and then we're going to look at the AC performance of the device, and then finally wrap up with some development tools and how they can be used to develop for RFSoC applications. I'm Rodger Hosking. I'm going to start the first part, which is the overview of the RFSoC chip itself. This is a chip that was, it's an FPGA in the Zinc UltraScale Plus family of Xilinx FPGA products that has some remarkable features. It includes 8 A to D converters and 8 D to A converters at sampling rates above 4 gigahertz each. It has a complete multi-core ARM processor subsystem, and it has, of course, the FPGA fabric in the UltraScale Plus family. It has lots of powerful high-speed I/O features like dual 100 gigabit Ethernet that we can adapt to through optical or other connections. So it's a complete chip solution to RF I/O applications. Very powerful. So what does this do to the market? Well, first of all, because if you can look at that diagram down below, you can see that what the RFSoC chip does is it replaces a whole bunch of discrete components, and it saves you about 50% in size, about 30 to 40% in power, 40 to 60% of the cost savings, and then, of course, it's much lower in latency, which has to do with how long it takes to go from the A to D to the D to A. This is very important for countermeasure applications. So what does this mean to the market? Well, it really means a lot of things are possible that weren't before. First of all, it allows you to get software-defined radio functions closer to the antenna. It gives more capabilities for unmanned aerial vehicles. You have smarter devices in smaller spaces. You have much more higher density support for phased array applications, which is extremely common, better dynamic range, and the lower latency for countermeasures we mentioned before. It really also supports remote sensing and conversion, where you can put this chip right up next to an antenna for some very, very close, getting very close to the antenna with your signal processing solutions. And then lastly, it opens up a lot of new applications that previously might have been physically or economically unfeasible with the discrete solutions that otherwise you'd have to use. But it does have the RFSoC, because it has all these different interfaces, analog and digital, high-frequency RF, and clock signals, all going into the same physical chip. It has an extreme set of rules that must be maintained in order to keep these RF signals clean from contamination with the other high-speed digital signals, The power supplies have to be very well filtered and regulated. The chip itself requires 13 different power supplies. The ARM processor has a lot of I/O, including gigabit Ethernet. And, of course, you have 2 different banks of DDR4 memory running at 2400 megahertz. So there's a lot of design issues that have to be taken care of in order to make sure that you get the successful use of the capabilities of the chip. So in order to help our customers do that, we came up with a concept of the Quartz XM RFSoC Express module. What it has is it has all of the critical connections to the chip itself brought out to very convenient-to-use connectors that will allow customers to take the RFSoC functions and much more easily embed them into custom applications, custom carrier boards, without having to worry about so many of the problems that we enumerated before, including, for example, all 13 power supplies are now on the same chip, on the same board rather, and all you need to do is supply 12 volts. High bandwidth analog connectors, high bandwidth digital connectors for the 28 gigabit serial lines, for the dual 100 gigabit Ethernet ports as well. So it's really quite a nice solution that we came up with. And here's a block diagram showing you, again, all of the features that surround the RFSoC chip that are on this Quartz XM Express module. So, and you can see from that little thumbnail drawing at the bottom how small this module is. So it makes it very easy for you to incorporate it, or multiple copies of it, in a very small space to fit into space-constrained and size, weight, and power-constrained applications, which is really common in a lot of military applications especially. What we do to make it easier for our customers to use the module is that we provide a complete Quartz XM carrier design package, which includes all the documentation, including complete schematics, diagrams, printed circuit board layers, and so forth for our 3U VPX carrier that takes the Quartz XM module and makes it a complete 3U VPX board, both in air-cooled and conduction-cooled. So the kit includes the definition of the Quartz XM module pins, the location, 3D models, thermal models, and so forth, along with software and operating system and instructions for how to get all this working. And we also do a design review of your custom design to help you make sure that you catch all the little things that could happen in your design, because we've been through it before and we're kind of experts in it. An example of what you might do with this, for example, is to take 8 of the Quartz XM modules and put them on a single printed circuit board to implement a 64-channel phased array planar antenna system, where you can make rather direct connections from the antenna elements through some RF circuitry directly into each of these 8-channel Quartz XM modules to give a very compact, very powerful solution for these kinds of applications. And yet there are many other applications like unmanned vehicles, missiles, airborne, landborne, airborne, all kinds of different platforms that can take advantage of the small size, weight, and power that the RFSoC module offers to the market. So that's really our story on the hardware side. What I'd like to do is to let Paul Mesboff take over and tell you how well this device really works in terms of its AC performance. Paul, I'll turn it over to you.
That way, I'll go this way. Okay. Well, thanks everybody for attending. I did a lot of measurement over the last year of performance of RFSoC. At first, I was skeptical that we would get the performance that we seem to be getting, because you've got 8 4 gigahertz 12-bit A to Ds and 8 6.4 gigahertz 14-bit D to As jammed into a small place. I was pretty pleased when I saw the performance. These following few slides are excerpts from a much larger report that I prepared that's available from Pentec if you wanted to actually look through it and see the kind of performance that you can expect. So just a couple of charts. We've got 400 megahertz. You can sort of see every one of these spur-free dynamic range plots actually is being performed with a filter, bandpass filter, that rejects the signal generator's harmonics. So the things that you're actually seeing are the actual performance of the RFSoC, and you can sort of see that the 400 megahertz, you've got spectacular performance, sort of better than 80 dB. As the frequency rises, you can expect to see a little bit of rise of harmonic distortion. Here at 900 megahertz, you're about 70 dB. That little noise hump that you see in there is actually signal generator noise, but it's shaped by the shape of the bandpass filter. This next slide is at 1200 megahertz. Again, you can sort of see the noise shape, but indeed, we're still, pretty respectable harmonic distortion here. Two-tone is really terrific. You can sort of see at these frequencies, better than 80 dB. Again, the linearity of this device is pretty spectacular, and I'm very pleased. But in addition to linearity, the noise spectral density. In fact, this slide, which says A to D noise and spurious pickup, essentially that spurious is not really pickup. That's actually calibration artifacts. Again, they're pretty far down, certainly below 80 dB. And if you look at the noise spectral density of minus 155 dBFS per hertz, that's in fact even a little bit better than what Xilinx publishes as their typical performance. So we're really doing pretty great, and ultimately what we need to be able to do to perform. We have a little bit of DAC performance here as well. What you can see here, because this is the output of a spectrum analyzer, what you can see here is the performance through a pretty wide span. If I go ahead and advance it to focus on where the second harmonic was, you can sort of see at 768 megahertz, the second harmonic was down below about 70 dB. And so that's just a brief overview of the spur-free dynamic range and noise spectral density that you get from these converters. But one of the things that enables this to happen, before we get there, I did want to actually add a little refinement to something that Rodger had talked about, and that is the A to D and D to A latency. What we actually are showing here is a oscilloscope shot, which is actually presenting a pulse signal applied to the input, and then of course the output of the D to A converter. And that latency was pretty small, at 145 nanoseconds. That's and of course this was both the A to D and the D to A were sampling it at 4 gigahertz. And that's pretty good. If you compared that to a discrete implementation of JESD 204B interconnected A to Ds and D to As, it's probably an order of magnitude or even 2 orders of magnitude better. Now we're going to go to the other thing that makes all of this possible, and that has to do with Xilinx's embedded calibration scheme. And they have what's called a foreground and then a background calibration. And they require, during foreground calibration, this exists at the beginning of software initialization, they have a requirement that there is no input signal energy applied at all. And then during background calibration, they require there to be at least about minus 40 dB below full scale of signal energy, and it has to last for at least 100 microseconds. Now, these requirements, if they are met, give you spectacular performance, as I've indicated before, in linearity, but they're hard to meet because real-world signals sometimes will not operate that way, especially if you consider radar signals, which, of course, could have low duty cycles. So Pentec has actually implemented both hardware, circuitry, and IP to mitigate that, and therefore we're able to preserve calibration even while signals can come and go, and the user doesn't have to worry about it. And I can sort of show you, as my last 2 slides, the results of calibration being on and off. Here, there's no calibration. You can sort of see the sidebands that are a result of the nonlinearities. As soon as our calibration circuitry is applied, those sidebands immediately attenuate. So it's a pretty great arrangement, both from Xilinx and the enhancements that Pentec has provided, so that you can enjoy the benefits of this calibration and the linearity that it gives you. So at this point, I'm going to turn the presentation over to Bob Scandura. I'm sorry about some momentary web interconnect problems, but I think we're back online. So Bob, with no further ado, is going to talk about some development tools regime.
Thanks, Paul. So this product, as well as all of our products, ships with is delivered with a complete suite of functions, and they're provided as IP inside the FPGA. And the idea is that many of our customers will take the product and just plug it in and use it. Probably more customers, 85, 90%, will actually go in and modify that FPGA code because they'll modify it for what they need in their application. But I wanted to give you a quick view of some of the built-in functions that this board ships with, because it really does encompass a lot of the things that you might need to do when you're developing. This block diagram inside the kind of the peach-colored box, which is the FPGA, are white boxes. Those are all IP cores that we have installed, we provide to you, that do a lot of these, actually all these functions. So this is a little bit of a busy slide, but if you follow through the green lines, what you see is that A to D data coming in can be routed through to, let's say, the DDR memory, where you can grab snapshots of the data, or you can route it out through the PCIe to get to, let's say, a host computer where you're recording it or looking at it. The purple lines represent a higher speed path. What that allows you to do is stream, let's say, the 4 gigahertz data straight through to the 100 gigabit Ethernet interfaces. And the whole thing with that is that you're generating a lot of data with the 4 gigahertz A to Ds. This is the fastest way to get the data off the board. There are 2 built-in 100 gigi interfaces. They're running better than 12 gigabytes per second in terms of data transfers, so you can get a lot of data off the board that way. In addition to those, inside those cores are things like the data acquisition engine, and that lets you set up triggers, it lets you set up gates, it lets you trigger off of time. There's a lot of different features built in. There are additional digital down converter cores. You can tag the data with channel and time information using our Vita 49.2 core. These are all blocks that are built into the basic functionality of the board. The second slide is the D to A direction, and I didn't animate this one, but basically we have paths. You can bring data into the board, go into the onboard memory and put waveforms in there. You could create a waveform table and then have the waveform generator IP send that out to DAC as required. You could do it with triggers. You could have multiple waveforms in there. There's another path to bring data in through the 100 gig E. And then there's also a signal generator, which can generate simple test signals, but it's also set up to do radar chirps, which is very convenient. So that way, what you can do is you can set that up and actually use this for a radar test bed or as part of your radar application. Now, there's 2 pieces to this puzzle. There's the software that is being used for creating the IP, which, again, we provide. Everything I just showed you is provided as IP blocks. So you have access to that to either modify or use as you need. And that's all VHDL source. It's complete documentation, so you really have everything you need to work with it. That works within Vivado. And then the other side of it is the Navigator board support package. These are our 2 software tools, Navigator FDK or FPGA design kit and the board support package. The BSP are all the libraries you need to access the board and control it. So these are C libraries. We provide them basically a one-to-one relationship. So every IP core that you've just seen has a software controller on the other side. And you might be running the software on a host, or because the RFSoC has an ARM processor, you might be running the software you create right within the ARM. Just to show you how the Navigator toolset works within Vivado, anybody who's using Xilinx FPGAs is familiar with the Vivado interface. What we did is we made sure that our Navigator core, or our Navigator FPGA design kit, actually comes into Vivado as a project. So what you're seeing in the slide, I hope you can see it, is the block diagram of the entire design. And the idea is you can go in there and you can use it as is. You can start replacing blocks. There are about 140 different cores that we provide as part of this. and you can modify those as needed. And the idea is very simple. You know, this stuff isn't easy. There's a lot involved in generating this IP. So the whole idea is to get you as far along as we can with built-in IP, and then you can modify just the parts you need. That way, all the plumbing and all of the DMAs and all the functions that you wouldn't want to have to design from scratch are in there. You're just going in and kind of putting in your secret sauce to finish the application. So that's what I had for slides. So I guess if we want to go into questions.
I think that would be a good time if
Carlos has any questions that came in.
Yes, we will be going to our Q&A now. A few of you have already submitted questions, so we're going to jump right in. If you'd like to submit a question, type the question into the question window on the side of your screen and hit the submit button. While we're answering questions, please complete the feedback form, which is located on the bottom of your screen. We apologize for the technical difficulties we experienced during today's webinar. Please remember that the slides are available for download in the resource area. Our first question: can the RFSoC generate and receive radar pulses?
Yes, the answer is it can, and in fact, the whole idea of having both the A to D and the D to A converter gives it that full in and out capability with bandwidths capable of being close to 1.5 or 1.6 gigahertz. So you can build a receive-transmit radar system with extremely wide bandwidths, and you get 8 channels of transmit-receive in a single RFSoC chip, which then, of course, also occupies a very small space, as we saw with the Quartz XM module.
Thank you. Our next question is, how do I get all of that ADC data off the RFSoC chip?
I can take this one. There's 2 ways of getting it off the chip. We have a 8X PCI Express Gen 3 interface, and that would give you perhaps a sustained data rate of a little bit over 6 gigabytes per second, and that's nowhere near what you would need. What Bob had actually mentioned a few minutes ago is that we have 2 100 gig Ethernet interfaces, and that would give you an aggregate of almost 24 gigabytes per second, and that's probably the best way to get data off of the chip. Interestingly enough, we've got 64 gigabytes per second worth of data being produced by those 8 12-bit A to Ds. So really, it's a challenge to move all the data on and off. And for those systems, such as radars that have duty cycles that are less than 100%, then you're going to use. That's the way you can capture snapshots of data at the full rate internally, and we're capturing that into the block RAM inside the RFSoC FPGA fabric.
Thank you. Our next question is, can Pentex supply a development chassis for the RFSoC products?
Yeah, I'll take it, sure. We do. We actually have a very simple, low-cost chassis that provides power to the board. So you put the board in there, it provides power and cooling. Because the ARM processor is built in, you really are doing a lot of your debugging right on the RFSoC itself. So what you end up doing is just connecting a notebook computer to it, and you have the tools installed there. And you have this development chassis. It's our model 8257, and that's a development chassis for RFSoC.
How much power does the RFSoC draw?
That's a great question. Currently, our model 5950, which is a 3U VPX card, the total draw with the IP that we include in the factory installed configuration, the total is about 52 watts. The RFSoC module itself is about 41 watts, and the RFSoC chip contribution to that is 28 watts.
And that's with all the A to Ds running.
And that's with all the A to Ds running, the D to A's running. It's certainly power hungry, but we have sufficient power generation capability on the board and pretty terrific thermal management techniques.
Thank you. The next question reads, is the Pentec calibration circuitry in the Quartz XM module?
That's a really very interesting question. And the answer to that is it takes two parts. It takes some hardware circuitry, and that hardware circuitry is not in the the Quartz XM module. It's on the carrier for it. And then it, of course, takes some IP. And the IP is pretty sophisticated, and that is indeed, of course, on the Quartz XM module.
Our next question is, how does the 3U VPX board deliver 100 GBE signals?
Well, the way we have that connected is by using one of the VPX standards, OpenVPX standards, which is called VITA 66.4, which gives you optical lanes that come out through optical to electrical transceivers on our 5950 carrier board, so that we are engaging with blind-made optical connectors. As soon as the board is plugged in, it connects up to optical links, and in this case we have 2x4 or 4-lane optical lanes going for each of the two 100 gigabit Ethernet connections right out to the rear panel, which is a very popular MPO connector that can then be connected up to any network switch compatible with 100 gigabit Ethernet.
If we are using Pentec I apologize.
No, that's okay. Go ahead.
If we are using Pentec IP as the foundation of our application, how is that licensed, and are there royalties?
I'll take that.
Okay.
Because I just actually left that out when I described it. All of the IP that I showed you comes with the FPGA design kit. And again, you get access to all that. What's great about it is that you just buy the kit once, and as long as you're developing for a Pentec product, there's no recurring licensing fees. There's no additional cost at all. You just use that IP as part of your application, and it's included in the purchase. So that's really nice.
We have a few more questions here. Can I use the RFSoC ADs at lower sample rates at 4 gigahertz?
I can handle that. Yes, you can lower the lowest sample rate that RFSoC is specified to work at is 1 gigahertz. So you can lower the sample rate by lowering the frequency that is produced by our fractional end frequency synthesizer, which is a low phase noise sample clock generator. But you can't lower it below 1 gigahertz. However, we do include extra stages of digital decimation, and that, of course, can provide a filtered output of a reduced sample rate. And then it is always possible in your own IP simply to throw out samples, and then you could, of course, lower the sample rate as an integer submultiple of the lowest sample rate to whatever you would like.
Thank you. Our next question is, what is the maximum decimation for the DDCs?
I'll take that. Following up to Paul's last answer, inside the RFSoC chip itself, the decimation is by 2, by 4, or by 8. But in the FPGA fabric of the RFSoC, we have implemented an additional by 16 decimation to get you a decimation all the way up to 128. And this gives our customers flexibility to take some very wideband inputs with no decimation all the way up to decimations of 128 without having to do any FPGA design. On the other hand, they can add and extend the decimation factors by adding rather simple decimation filters in addition to the ones that we provide and Xilinx provides in the chip.
And just to add a little bit of flavor to Rodger's answer, the decimations available inside the RFSoC A to D converters themselves are actually part of a digital down converter infrastructure, which includes a frequency shift capability and a complex output. So this is really a digital tuner capability, and of course the D to A's have a complementary digital up conversion capability as well.
Thank you. Our next question reads, how do you cool your RFSoC products?
They are cool. They really are cool. Oh, how do we cool them? Yeah. Now, this is pursuant to my comments about power. So on the 5950, which is the 3UVPX carrier for our Cortex-M module, there is a very sophisticated heat spreading plate that we have that, in addition to providing simply the raw metallic method of moving heat through the card edges, it also has a unique set of interior air channels so that we can enhance the cooling. And that's the main heat spreader. External to that, there are plates on both the top and bottom of the entire assembly that unify the heat management capability so that all radiative surfaces of the board can conduct the heat out to the card edges.
So we're running up on time, gentlemen, so our last question will be, if we need support during development, how much is included? Are we able to submit requests for support via email, webcast?
I'll take the easy question. You have free lifetime support, and it's free. So once you purchase our product, you can call us, you can email us, you don't have to set up a web case, you will end up talking to an engineer on the phone, which is great. And that support isn't just for the hardware, it's for the software. We have questions coming in all the time for FPGA support, and that's all included when you purchase the product. Excellent.
Well, thank you so much, gentlemen. Again, we like to apologize for the technical difficulties that we had before. If you missed any of the slides during the presentation, they are available for download. So please make sure that you do that as a reference for you. On the behalf of Microwaves and RF Design and Electronic Design, I'd like to thank Pentec for sponsoring today's event, and of course all of you for joining us. Have a great rest of the day.
Thank you.
Thank you. Thank you.